Hello there, and welcome to another calculus video. Last time you watched a video is likely on intervals of increase and decrease, where we found changes in signs of the first derivative of a function. And now we're going to do basically the same thing, except we're doing it for the second derivative, because we're going to look at concavity. All right, so if you compare the notes, they probably look almost identical, because guess what? I use some of the same graphs. So let's do it. If you want to find intervals of concavity, concavity of f comes from the sign of f double prime. So if I want to know about f's concavity, I need to know the sign of f double prime. And I'm going to move the video camera back because my face is really close and it's freaking me out. So this one says, given here is the graph of f double prime of x. All right, thank you. On what intervals within 0 to 8 is f concave up or down? Well, I just told you. If you want to find intervals of f, you look at the sign of f double prime. So within the interval from 0 to 8, f double prime is negative from 0 to 1. It is positive from 1 to 3. It is positive from 3 to 5. It is negative from 5 to 7. And it looks like from 7 to 8, it's going to be positive again. So from 0 to 1, f is concave down, because f double prime is negative. Now, you might notice that I did an open interval. Concavity is always on open intervals. Intervals of increase and decrease are often on closed intervals, but concavity, always open, all right? So 0 to 1, we're concave down, and you know what? Let's just do the other concave down right now. That's from 5 to 7. And then from 1 to 3, and from 3 to 5, f is concave up because f double prime is positive. Ta-da. Quick reminder about concavity. When concavity changes, we call that a point of inflection. So if f has a point that has a tangent line, okay, that's a condition that doesn't come up often, but it's semi-important. If f has a point that has a tangent line, so f exists and is smooth, then that point is a point of inflection if the concavity changes there. Well, how do I know if concavity changes? If the second derivative changes sign. So what x values are inflection points for f of x? Well, let's see. Concavity changes sign when f double prime crosses the x-axis, which is there at 1, and then again at 5, and then again at 7. And I forgot to write 7 to 8 over here, my bad. So what x values are inflection points of f of x? That would be x equals 1, 5, and 7, because f double prime changes sign. Okie dokie. Now, that's pretty easy when you have a graph of f double prime, but what if you have an equation for f double prime? It's still the same rules. F is concave up when f double prime is positive. F is concave down when f double prime is negative. You want to know when the positives and negatives are? You got to find the zeros first. So if you want to find concavity, you find any values where f double prime equals 0 or does not exist, and you find any domain restrictions for f. Then you segment that domain into pieces, sometimes using a number line to help you. Then you determine the sign of f double prime at one point within each interval, and then you use those signs to find your concavity. That's it. Okay. F, let's see, find the intervals where the function g is negative 2x cubed plus 6x squared minus 3 is concave up and or down. Indicate the x coordinates of any points of inflection. All right. So if I want to know about concavity, I want to look at the second derivative. So g is negative 2x cubed plus 6x squared minus 3, making g prime negative 6x squared plus 12x. Making g double prime negative 12x plus 12. And I want to know when g double prime changes sign, so I got to start by finding when it equals 0 or doesn't exist. And that's going to happen at x equals 1. And it always exists. And so then I say, okay, g of x is a polynomial, so its domain is all real numbers. And it seems to only have a second derivative that equals 0 once. So I'm going to go from negative infinity to 1, and from 1 to infinity. So my concavity is something from negative infinity to 1, and my concavity is something from 1 to infinity. To figure out that concavity, I need to test in the second derivative one of those values. So a number between negative infinity and 1 would be 0. F double prime of 0 is going to be negative 12 times 0 plus 12. That's positive. So F is concave up. And then if I do F double prime of 2, let's see, negative 12 times 2 is negative 24, plus 12 is negative, which means F is concave down. And I'd like to say that this was an intentional mistake, but it wasn't. I've been writing F instead of G. Does that matter? The long answer is, yeah, it kind of does, but it depends on what else is going on. The short answer is try not to make that mistake, and if and when you notice, go back and change your F's into the G's that they are supposed to be. Now, if on a test, say my test or an AP exam or something like that, you rename G as F, as long as there's not another function F in the same question, it's fine. Everybody knows what you're talking about. We just default to F. But if there's a question that says F is doing these things and G is doing those things, and then you accidentally start spelling G as F of X, then it's going to be a problem. All right, so I fixed it. G is concave up, G is concave down, and then it says indicate the X coordinates of any points of inflection. An inflection point is going to be where the second derivative changes. Our second derivative does change at X equals 1. So X equals 1 is the location of a point of inflection. Moving on. The next one says G of X is X minus 2 to the 4th minus 9. Find the intervals of increase and decrease and any relative extrema. Then find the intervals of concavity and state any points of inflection. If you want to pause here and just do this yourself and scrub through the video to check, by all means. So I'm going to do the thing. I have another G. I want intervals of increase and decrease, which means I need to be looking at F prime. Oh, look, I did it again. G prime. Okay. So let's see. G is X minus 2 to the 4th minus 9, making G prime 4X minus 2 cubed times 1, because it's technically a chain rule. Derivative of the outside, keep the inside, times the derivative of the inside. And I want to know when G prime equals 0 or doesn't exist. Well, it always exists, and it's going to equal 0 when X is 2. And so then from negative infinity to 2, G's doing something, and from 2 to infinity, G's doing something. So G prime of 0, which is between negative infinity and 2, G prime of 0 is going to be 4 times negative 2 cubed, which is negative, times 1. So G prime of 0 is going to be negative, which means G is decreasing. And then G prime of, let's say, 5 is going to be 4 times 3 cubed times 1. That's positive. So G is increasing there. And again, just as a reminder, I'm plugging 0 into G prime. I'm plugging 5 into G prime. So there's my intervals of increase and decrease, and then it says find any relative extrema. Well, G went from decrease to increase. So right in between there, we had a relative min at X equals 2. Then the next part says find the intervals of concavity. So if I want concavity, I need G double prime. So G double prime, it's going to be another chain rule, 12 times X minus 2 squared times 1 equals 0 or doesn't exist, but it always exists, and it equals 0 at 2 again. So from negative infinity to 2, it has a concavity. From 2 to infinity, it has a concavity. G double prime of 0. Let's see, I plug 0 into G double prime. That's 12 times negative 2 squared. That's a positive. So G is concave up. And then G double prime of 5, again, I'm going to plug 5 into here, is 12 times 5 minus 2 squared. That's positive. So G is concave up. And then it says state the coordinates of any points of inflection. A point of inflection is where concavity changes. Our concavity did not change. So there are no points of inflection. Okay? And then last but not least, it says state the x coordinates of any points of inflection for h of x if h double prime is that factored thing. Okay, well, if I want points of inflection for h, I need to know when h double prime changes sign. Fortunately for us, they gave us h double prime. And so h double prime changes sign when the graph of h double prime crosses the x-axis. But you might be thinking, well, but we don't have a graph. But I'm betting in Algebra 2 or Pre-Calc, you spent a long time talking about graphs of factored polynomials and their multiplicities. And so either in your head or in reality, we could graph h double prime and do a pretty good job of it. So let's see, 7x, that means h double prime has a 0 at 0. X minus 2 squared, that means h double prime has a 0 at 2. X minus 5 cubed, that means h double prime has a 0 at 5. X plus 4, h double prime has a 0 at negative 4. X minus 8, h double prime has a 0 at 8. And let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 19. This is a polynomial of degree 19, which means its end behaviors are different, and it has a positive lead coefficient, so it goes from low to high. All right, so now let's graph this thing. X plus 4 is raised to the 4th, which means that our first 0 has a multiplicity of 4. More specifically, it has an even multiplicity. So h double prime is going to come here and boonk, bounce off. 7x to the 1st. The multiplicity at 0 is odd, and it's only raised to the 1st. So it's going to go straight through that 0. X minus 2 is to the 2nd. That is an even multiplicity. So we're going to bounce off, boonk, 2. X minus 5 cubed. 5 has an odd multiplicity that's not 1, so it crosses with inflection. So we're going to come down here, flatten out, and then keep going. X minus 8 to the 9th is odd. So that's going to cross with inflection. And if you're right now having a light bulb breaking moment going, wait a minute, crosses with inflection, now I know what inflection means. Hey, look, when something crosses with inflection, that means the graph goes from being concave something, in this case down, pardon me, Jesus, Mrs. Fibber. When it crosses with inflection, I'm so sorry, when it crosses with inflection, it goes from being concave something to concave something else. It is concave down on the right, but it was concave up on the left. Because if you look right here, this left-hand side, sorry, my screen is jumpy. Gonna give everybody motion sickness. If I look from the left-hand side of 5, that's concave up. And if I look from the right side of 5, that's concave down. That's what crosses with inflection is always meant. Okay? But I digress. When do we have points of inflection? The whole question was, when do we have points of inflection for H? Well, H has points of inflection when H double prime crosses the x-axis, and that's going to be at 0, and at 5, and at 8. So I kind of went in the weeds there on like, ooh, crossing with inflection. We're talking about inflection, but what do I really need you to know after today? I need you to know that if you want to find points of inflection, it's where the second derivative changes sign. And if you want to do that kind of stuff algebraically, you need to find your second derivative, set it equal to 0, and then make intervals to figure out what your concavity is and whether or not it changes. And that's it. I'm done. So I hope you are having a lovely day. It is rainy and gross outside here, but I hope your day is better than that. Have a good one. See you in class.